It is now time to actually do statistics. We define statistics as the use of limited information, samples, to make inferences about the larger population from which the sample was drawn. Just how the sample was drawn is an important matter. If we sampled students in a stat class to determine the attitudes of Oklahomans towards a tuition increase, no one would consider the results valid. This sample may be a good representation of students' attitudes at OU, but certainly would be a biased reflection of those for all citizens in the state. In all that we do in this class, it is always assumed that any sample is randomly drawn. This may be a very wrong-headed assumption in actual practice, but if the sample is not random, then all statistical theory is invalid. Only those samples with bias built in a known way, called stratified or targeted sampling, can be used in making statistical inferences. As an example, political polling is done with stratified samples based upon past political party preferences to determine if there is any movement away from past choices. All other non-random samples cannot be used effectively for making inferences about the underlying population. Techniques for testing if a sample is random and for drawing random samples comprises whole college courses. In economic statistics, most economic data is generated in a way that assures randomness or approximate randomness, and thus we will operate on the assumption that we are always dealing with a random sample. This is always an important issue to check before analysis of any data set, however. So, in order to do inferential statistics, we will have to make do on the basis of samples from the population. The reasons we have to rely upon samples from a population are obvious. The time and expense of checking every invoice to determine its validity, or every shipment to see if it contains all the items, may well exceed the cost of errors in billing or shipping. For some products, sampling would require destroying them. Consider trying to determine if the batteries produced all have the life expectancy as advertised. This raises an important question. Just which sample did we draw? In this unit, we will look at the sample in a very different way than we did in the past. We will begin to consider a sample as one possible observation from a set of almost infinite possible samples we could have drawn. This will give rise to probably the most important theorem in all of mathematical statistics, the central limit theorem. Remember that we studied probability because we can calculate exact probabilities in the world of known parameters and distributions. But in the world of inferential statistics, we have precious few resources. The central limit theorem allows us to convert statistics problems into probability problems. All we need to know to calculate probabilities is the underlying distribution and the mean and standard deviation of that distribution. That is what the central limit theorem provides. By the end of this unit, you will be able to recognize the role of the central limit theorem plays in inferential statistics, classify continuous word problems by their distributions, as well as apply and interpret the central limit theorem for means, and understand the relationship between the sample size and the standard deviation of the sample distribution. This is the transition, and this theorem is the bridge that we will cross to find solutions to the questions that people want statistics to answer.